Are you a data scientist? Do your tools make it easy to track your experiments, deploy to a machine learning model to production, and manage a GPU cluster? This free book from O'Reilly can teach you how to do all that. It's about tuning neural nets, making them scale, and then deploying them to the real world.
Hello world, it's Siraj, and neuroscience and machine learning, two different fields that are actually very much connected. Today I'm going to talk about how neuroscience and machine learning are very connected. I'm going to talk about how recent advances in neuroscience will move machine learning forward. And before I talk about that, I want to show you a demo. And this demo is an interactive network visualization tool for exploring functional brain connectivity. It's called SpectraViz. And after this video, you're probably going to want to look at more neuroimaging techniques, and this is a great way to get started. I found this repository on GitHub, and basically what it allows you to do is simulate a brain in silico. But it's a very, it's not the full brain, obviously, but it's a good model of how neuroimaging tools can be simple. And it was created using D3.js, very cool visualization library. You can hit start, and you can see the network just move. It's very cool. But I just wanted to show you that really quickly, and you can switch the timing, the frequency of connections, all these different things. You get all of these different mappings of how the neurons are moving, how they're interacting in the network. It's pretty cool. So check out that after this. The link to that is going to be in the video description. But let's get started with this. I've divided this talk into three different parts: the history of neuroscience and AI, contemporary neuroscience and AI, and the future of neuroscience and AI. Okay, so let's start off with the history. And obviously I've got this super generic image that is shown everywhere, but the idea of this image is saying, hey, we've got this neural network, and what it was inspired by is the human brain. Okay, so at the dawn of the computer age, when computer science was invented, when it was starting up, all of AI research was neuroscience. Everything was based off of neuroscience. It was the same thing. Every single discovery came from neuroscience when it came to AI. And the early pioneers of this field straddled both neuroscience and AI. They were connected to both. Collaborations between all of these different fields was highly productive. So let's look at some examples here. How can I talk about computer science without talking about Turing, right? Turing was the man. Turing test. Okay, he invented the Turing test. He invented a bunch of stuff, but he's in a lot of ways the father of computer science. But the idea behind the Turing test was, let's see if a human can tell if he's talking to either a human or a machine. And if he can't tell, then the computer has passed the Turing test, right? Turing was very, very, very much into the brain. He said, we are not interested in the fact that the brain has the consistency of cold porridge. That was his quote, but what he meant was he was very interested in how the brain worked. He was very certain that it was a very complex organ, and his view is shared by many in that we cannot represent the brain using anything but math because it's such a complex system, right? Think about the brain as a graph, right? Think of it as a graph. And if you think of it as a graph, you have these neurons, nodes, connected to each other. It's this combinatorial explosion, right? In terms of a search space. When you take a signal and you propagate it forward, it's going to be split up into hundreds, if not millions of different signals for different neurons. And this is a combinatorial explosion, right? There's no way to describe this via colors or, regions other than by sheer beautiful math, right? And if you think about math, right? There's this idea of this mythical book, the book of math, that when you die, God is able to show you this book. And it has all of the theorems for everything listed out, right? And so when you die, you're able to see, oh, this was a theorem, this was a theorem. And over time, we humans have been able to discover some of those theorems, but there are a lot more we haven't discovered. Now imagine a book of AI, right? In a book of AI, neural networks and deep learning would be one of those theorems, but there are way more that we still have to understand and to find, right? To discover. Neuroscience is a great way to do that, right? So Turing, he had this computer program that he invented at the University of Manchester that accepted a single input, right? A single number as input and output a single number. And he wagered, and this is another famous thing by Turing, Turing's wager, that it would take someone 1,000 years to figure out how that black box worked, how that number converted from one from one integer to another. And then he said, he extrapolated from that idea, and he said, well, if you think about the brain as that black box, it's going to take a really, really long time to figure out how that works. And so he was very skeptical that we would be able to figure out how the brain worked, even though most of his work involved trying to recreate the brain in silico. But if Turing could have just seen the modern supercomputers that we have, the advances in neuroimaging techniques that we have, he would have been blown away, right? So yeah, it's definitely possible to recreate the brain in silico. But let's keep going here. So McCulloch and Pitts, two other neuroscientists, right? They invented the model of the single neuron. Now, this is where it all started. They wanted to create some sort of mathematical model that represented how a neuron works. And this was a very basic model. The model said this: let's take some inputs, right? Some set of numbers, x like it's represented here. Let's apply some sort of function to that, and output is one single integer, right? That is something like what a neuron does. It's accepting these inputs, these signals, right? It's doing something to those signals, and then it's outputting a signal, and that signal propagates to other neurons, and that creates this network, this neural network of neurons, right? And then they kept going, right? So then Hopfield took this idea and he said, let me take the McCulloch-Pitts neuron, let me combine them together so the outputs of one neuron are fed as the inputs of the next neuron, and let's just keep doing that over and over again. And so this was called the Hopfield network, right? So this was the first recurrent artificial network. He connected McCulloch-Pitts neurons together. Then came Hinton, right? So Hinton said, okay, we've got these layers of neurons. What is the best way to optimize these neurons so that it can complete its objective, right? And so he invented with his colleagues the backpropagation technique, which said, we've got some output prediction. Let's compute the error based on what their label is. That's the error value. Let's compute a gradient, and the gradient says how much to update the weights of the network over time. Let's update those weights incrementally backwards in the reverse direction as we forward propagate the input data. And this is called backpropagation. And Hinton was also a huge proponent of a neuroscience level of thinking when applied to neural networks in machine learning, right? During the AI winter, when everyone said he was crazy, he stuck to the idea of neural networks being a way forward in AI. And it turned out as seen in the deep learning revolution of late, that he was right. He was also a big proponent of neuroscience-inspired ideas like dropout, turning neurons on and off randomly to increase the generalization ability of a network, of nonlinearities, to allow a network to learn both linear and nonlinear functions, the idea of hierarchical and layered networks, etc., etc. And so all of this leads up until now. The problem with now is if you were to learn machine learning right now, if you were to learn about all the different types of models, support vector machines, random forests, decision trees, it's not very clear that all of these things are inspired by neuroscience, and in a lot of ways, they're not. So there's this disconnect between neuroscience and AI that didn't exist before. And what's happened is, because the discoveries in neuroscience have just grown and grown, and the discoveries in AI have grown and grown over time, these two fields have become so complex that it's hard for any one person to become an expert in both fields, let alone one. So it's hard to make any discoveries that intertwine these two. But the human brain is the only proof we have that this type of intelligence works. So it's yes, it's hard, but it's essential. It's essential to do. So Marr, this scientist had this idea of describing a biological system in 3 different parts. So one part was the implementation, the hardware of how this software is running, this wetware you can call it. Then there's the algorithmic part. What representations can implement such computations? And on top of that is the computational part. Why do things work the way they do? Equations on top of those initial algorithms. It's hard for us to work on the implementational part because creating hardware requires a lot of capital, right? Not everybody's got that money. So we need to focus on the algorithmic and the computational parts, and anyone with a laptop and GPUs in the cloud, so this is being democratized, can do that. So now let's talk about contemporary neuroscience, okay, and how it's played into AI. So there are 4 key areas in AI that have been affected by contemporary neuroscience. The first is attention, okay, so So the brain does not learn by implementing a single global optimization principle within a uniform and undifferentiated neural network. What I mean by that is it's not like we have some giant LSTM network running everywhere, right? It's not just some giant recurrent network. We have different modules that are good for doing different things. So one part of the brain could be doing something like a hop field network, and another one could be an LSTM network, and another one could be, a self-organizing map. And so there are different modules that are good for different things. And so up until now, for convolutional networks in particular, which are networks that are good for working with images, they work directly on entire images or video frames with equal priority given to all the image pixels. But we learned that the primate visual system works differently. Rather than processing all the inputs in parallel, visual attention shifts strategically. That's the key point here, strategically, among locations and objects, centering processing resources and representational coordinates on a series of regions in turn. And so recent AI discoveries have implemented this idea of an attention mechanism, of focusing on the parts that are most specific. And usually the way they do this is by having some weights for this attention mechanism that are updated via gradient descent over time. And so they're differentiable weights. And so the network learns where best to focus its attention on in whatever the input data is as it updates over time.
Riley can teach you how to do all that. It's about tuning neural nets, making them scale, and then deploying them to the real world. Riley can teach you how to do all that. It's about tuning neural nets, making them scale, and then deploying them to the real world. Riley can teach you how to do all that. It's about tuning neural nets, making them scale, and then deploying them to the real world. Riley can teach you how to do all that. It's about tuning neural nets, making them scale, and then deploying them to the real world.